Welcome to Elevate Learn. Today we're diving deep into Java Spring Security, one of the most critical skills for modern backend developers. Whether you're building a REST API, web application, or microservice, understanding how to properly authenticate users and authorize their actions is essential. In this tutorial, we'll explore authentication mechanisms, role-based access control, security filters, and real-world implementation patterns. By the end, you'll have a solid foundation to secure your Spring applications against common vulnerabilities. Here's our learning roadmap. We'll start with fundamental security concepts you need to understand before touching any code. Then we'll explore how Spring Security is architected internally, so you understand what's happening behind the scenes. Next, we'll get our hands dirty with practical authentication setup using Spring Boot. We'll cover role-based access control, which is essential for most real-world applications. Then we'll secure actual endpoints and explore best practices that professional developers use. Finally, we'll touch on testing to ensure your security is rock solid. Let's clarify two terms that are often confused: authentication and authorization. Authentication is about proving your identity. When you log into your email, you provide credentials, your username and password, to prove you're really you. Authorization comes next. Once the system knows who you are, it decides what you're allowed to do. Maybe you can read emails but not delete the entire mailbox. In Spring Security, we call the authenticated user a principal. The credentials are what you use to prove identity, and authorities or roles define your permissions. Think of it like an airport. Authentication is showing your ID at security. Authorization is your boarding pass determining which flight you can board. Spring Security works through several key components. At the core is the security context, which holds authentication information for the current request. It's stored in a thread local variable called security context holder, so each thread has its own security context. The authentication interface represents the authenticated principal and their authorities. When you try to log in, your request goes to an authentication manager, which coordinates the authentication process. Between you and the application sits a security filter chain, multiple filters that intercept requests and apply security rules. Finally, there's User Details Service, which loads user information from your database or any source. Think of it as a bridge between your user storage and Spring Security. Here's how requests flow through Spring Security. Every HTTP request first passes through a chain of filters before it reaches your controller. These filters work like security checkpoints. The authentication filters examine the request for credentials, maybe a username and password in a login form, or a bearer token in the authorization header. They extract these credentials and ask the authentication manager to verify them. If authentication succeeds, the request carries authentication information forward. Authorization filters then check if this authenticated user has permission to access the resource they're requesting. If any filter decides the request is invalid, it can reject it immediately. This layered approach means security is applied consistently across your entire application without cluttering your business logic. Now let's write our first Spring Security configuration. We create a class decorated with @configuration to tell Spring this is a configuration class. @enable web security activates security for our application, and @enable method security allows us to use security annotations on methods. The filter chain method returns a security filter chain bean that configures HTTP security. We specify authorization rules. Public endpoints are accessible to anyone, admin endpoints require the admin role, and everything else requires authentication. We configure form-based login with a custom login page and success redirect. Finally, we set up logout behavior. We also define a password encoder bean using bcrypt, which is industry standard for hashing passwords. This configuration becomes the foundation of our application security. When we run this configuration, Spring Security initializes several important components. The log shows that the security filter chain has been created with 15 filters. These filters are automatically added by Spring Security to handle authentication, authorization, CSRF protection, and other security concerns. The Authentication Manager is created and ready to process login requests. The password encoder is configured as bcrypt, which will be used whenever passwords are stored or verified. We also see the authorization rules being loaded into the chain. The application starts successfully on port 8080, ready to handle requests. Notice how many filters are automatically provided. This is the power of Spring Security. We don't have to write each filter ourselves. They're battle-tested, industry-standard implementations. Here's how we implement custom user loading logic. We create a custom user details service that implements Spring's user details service interface. When someone tries to log in, Spring calls our load user by username method with the provided username. We query our user repository to find the user in the database. If the user doesn't exist, we throw username not found exception, which tells Spring the login failed. If the user exists, we extract their roles and convert them to Spring's granted authority objects. Notice we prefix each role with role underscore, which is a Spring security convention. Finally, we return a Spring user object with the username, hashed password from the database, and authorities. Spring will automatically compare the provided password with this hashed password using our bcrypt password encoder. Let's trace what happens when a user logs in. First, the username password authentication filter intercepts the login request. It extracts the username and password from the form. Then it delegates to the authentication manager, which uses our custom user details service to load the user. Our service queries the database, finds the user, and converts their roles to authorities. The DAO authentication provider then uses bcrypt to compare the submitted password with the stored hash. If they match, authentication succeeds. The security context holder is updated with this authentication object, effectively logging the user in. The session is created, and the user is redirected to the success URL. This entire process happens automatically thanks to Spring Security's well-designed architecture. Now let's look at method-level security, which provides fine-grained control. The @preauthorize annotation checks authorization before the method executes. In our user controller, the getUser endpoint uses SPEL to express complex logic. A user can view their own profile, or if they're an admin, they can view anyone's profile. The createUser endpoint is restricted to admins only. The deleteUser endpoint requires admin role and ensures we can't delete the root user with ID 1. The getMyProfile endpoint simply requires authentication. This approach is powerful because authorization logic lives close to the business logic. You can use SPEL expressions to reference method parameters, authentication objects, and much more. Combined with URL-level security, this creates a comprehensive security model. Here's what happens when requests hit our secured endpoints. When user 5 requests their own profile at /API/users/5, the SPEL expression evaluates to true because the ID matches their principal ID, so access is granted. When the same user tries to access /API/users/3, the expression evaluates to false because they're neither the owner nor an admin, so Spring throws an access denied exception. When an admin tries to create a user, the has role check passes and the method executes. When an admin tries to delete the superuser with ID 1, the expression fails the end condition, protecting critical accounts. When an unauthenticated user tries to access their profile, they don't have any authentication, so the isAuthenticated check fails. This layered authorization prevents unauthorized access at the method level. Let's look at a realistic blog scenario. We have a blog where anyone can view published posts. No authentication needed for that. Authors and admins can create new posts. We use that authentication principle to inject the current user's details directly into the method. For updating posts, we use a custom security service method to check if the user is the author or an admin. Only admins can delete posts, ensuring authors can't delete each other's work. Notice how we use hasAnyRole to check multiple roles, and we use bean method calls in SPL for complex authorization logic. In the output, we see a reader successfully viewing posts, an author creating and editing their own posts, another author being denied access to someone else's post, and admins managing all content. This demonstrates how Spring Security handles real-world scenarios elegantly. Let's discuss critical mistakes developers make with security. The first mistake is storing passwords in plain text. This is catastrophic. If someone breaches your database, They have every user's password. Always hash passwords with bcrypt or similar. Second mistake, being too permissive with endpoint access. Some developers accidentally open sensitive endpoints with permit all. Always explicitly require authentication for protected resources. Third, trusting user input. Never assume client-side validation is sufficient. Always validate and sanitize server-side. Fourth, scattering security logic throughout your code. This makes it impossible to audit. Centralize security configuration in a dedicated class. Fifth, relying on client-side authentication. A user can manipulate their browser. Always verify permissions on the server. Spring Security makes these best practices easy to implement, so there's no excuse for ignoring them. Here's an important question. What happens when someone provides wrong credentials? Spring Security catches this at the filter level before it ever reaches your controller. An exception like bad credentials exception is thrown. The security filter chain short-circuits and doesn't pass the request forward. Instead, the user is redirected to your login page, usually with a query parameter like error equals login, which you can use to display an error message. This prevents sensitive information leakage. You don't want to tell attackers whether a username exists or if just the password was wrong. Spring handles all of this automatically, but it's important to understand the flow. This is a great question about security architecture. Many developers wonder if they should use URL-level security or method-level security. The answer is both. They work together beautifully. URL-level security, defined in your security filter chain, acts as the first line of defense. Requests that don't match the required roles are rejected immediately at the filter level, which is fast. Method-level security using at pre-authorize and similar annotations provides additional fine-grained control at the business logic layer. Both must pass for a request to succeed. This is called defense in depth. Even if someone somehow bypasses one layer, the other protects you. It's not redundant, it's good security architecture. Great question about thread safety. When a web server handles multiple concurrent requests, each runs in its own thread from a thread pool. If security context wasn't isolated, one user's authentication could leak to another user's request. A critical security vulnerability. Spring Security solves this with thread local storage. Each thread has its own security context. When authentication happens, it's stored in that specific thread's thread local variable. When the request completes, the thread's context is cleaned up. This ensures complete isolation. It's why Spring Security works reliably in high concurrency environments with thousands of simultaneous users. The thread local pattern is perfect for request-scoped data like authentication. Let's summarize what we've covered today. Authentication and authorization are distinct but complementary. Authentication proves who you are. Authorization determines what you can do. Spring Security's architecture is elegant. Filters intercept requests. Managers coordinate authentication. Context holders safely store authentication data. And service layers load user information. User Detail Service is your bridge to the authentication system. Security Filter Chain is the heart of Spring Security, and you configure it through Security Config. Method-level security with at pre-authorize allows you to express authorization logic right where your business rules live. The combination of URL-level and method-level security creates robust protection. Always hash passwords, never store them in plain text. Finally, thread local storage ensures your authentication data stays safe and isolated in multi-threaded environments. You now have the foundation to build secure Spring applications. Start with these basics, then explore advanced topics like JWT tokens, OAuth 2, and custom authentication providers.